Hello and welcome back to this Calculus 1 series. Today we're going to be covering one-sided limits and continuity. So, a really nice way to think, to first of all understand the idea of one-sided limits is to understand the greatest integer function. So what that is, if you're not familiar with it, is basically something like this. It's also called a step function, or amongst other things. So, how can you think of this? It basically means it equals to the greatest integer less than or equal to x. And just to give you some examples of values, it's basically greatest integer of 4, for example, is going to be 4. Greatest integer 4.1 is 4. And even 4.999 is going to be 4. So basically, any number that's, you're basically rounding to your ones place, essentially, in terms of positive numbers. In the case of negative numbers, let's say negative 4.5, you actually round down to negative 5, like that. And the graph of these types of functions, they're fun, but they look kind of like this. And I'm probably going to speed this up. So that's your general greatest integer function in its simplest form. And how you can understand this is basically for any of these x values, the function is going to be 1, for example. For x equals 1.5, you can see that it's just straight up going to be 1. Always, no matter what, you're basically rounding it down, like I explained before. And how you can apply this to the concept of one-sided limits, I kind of vaguely touched on it in the previous video, if you watched it. But basically, you need to take the limit as it approaches from either side of the function. So if you're taking, I'm going to choose, let's do x equals, as x approaches 3, of greatest integer value function of x. You have to solve for this. What you have to first do to take a one-sided limit, you have to take values that approach 3 from this side. 1 second. There we go. There we go. And from this side, like that. And you can see, it might be a bit obvious now that I say the arrows, it's not going to really exist. And that's simply because if you write it out in the one-sided limit notation, as I'm going to call it, like this represents as values of 3 that are less than 3 of that, I don't know what to call that. That's going to be 2. As you can see, you plug in 2.3, 2.4, 2.5, you're going to get 3 here. It's going to equal 2, sorry. And limit as x approaches 3 from the right side, or 3 plus of the function, it's going to be 3. And you might know this, it's pretty obvious, they're not equal, and that's why it doesn't exist, because you can't have a limit at a point that when the function approaches 2 different values at a said x value. Alright, that's the general idea. That's where you really use one-sided limits, is if you are deciphering a function and there's something weird happening. Even if it's an asymptote, asymptotes are actually great examples of one-sided limits, but of one-sided limits, because one side it's approaching to positive infinity, and on the other side it approaches negative infinity. That's what yields the asymptote. So with that, let's try to solve a problem using said one-sided limits. So limit as, let's see, f of x is going to be, wait 1 second, oops, sorry. Limit as x approaches 0 of f of x if f of x equals absolute value, greatest integer function of that for x less than 0 and sine x over x for x greater than 0. So for these types of functions, it kind of helps to graph it, and especially for wacky functions like this, you kind of have to use a graphing calculator, or in my case, Desmos, which is arguably the greatest human invention thus far. And let's just graph this real quick. I'm just going to hand graph it, and I'm probably going to speed this up as well. Okay, that took an obscenely long time, but that's fine. With the power of editing, you probably would never have noticed. So, let's take the one-sided limits of this function. So, it's going to be limit as x approaches 0 from the left side first. Doesn't really matter the order, you just do what pleases you. As x approaches 0 from the left side of f of x, and in this case you can see that's going to be 1. So this is our 0 here. We're going in from this side first, and you can see all of them point to 1. Okay, let's do the next one, and that's going to be, can't write, limit as x approaches 0 from the right side from f of x. And now you might be thinking that you'd have to use the sine of x function because you're using values that are greater than 0, and you would be correct in that assumption. So, as you might be familiar, or you might now be learning, there's a little rule here that's kind of a cheat code, but it's like this. Limit as x approaches 0 of this function, sine x over x, that's going to be 1. And you can just plug it in here. And that's just a rule, and you'll probably learn the derivation shortly, maybe in a few videos. But that's just a rule now. And therefore, since these are equal to each other, you can write the actual limit as f of x equals limit as x approaches 0 of f of x is going to be 1. And that's a pretty tame one-sided limits problem. So with that out of the way, let's cover continuity, which is a fun topic if you like solving for asymptotes or simplifying equations and stuff like that. Right, so you have a few types of continuity, or really discontinuity, really, because continuity is where the function exists everywhere. So really it could be called the three types of discontinuity, but you know, math is math and it's weird. So the first type is called removable discontinuity. And how how you can think about that is if your function has a hole, so something like this. Not like that. That's a continuous function. Something like this. Like that at point A. This is removable because you can have a piecewise function or something, and your actual function could exist somewhere up here or somewhere like that. It just means that you can't draw through it continuously. How I was taught is you can label a function continuous if you can draw it without lifting your pencil, and in this case you really can't because you have a value on the function that does not exist. It's not defined at. Yeah, and the, I guess, informal name for it is called hole. The second type of discontinuity is non-removable. And what this means is actually a good example of piecewise functions in non-continuous senses. I don't know. Will be something like this. Say you have a function like this. You have a hole there. Then it jumps down here. And it's defined here. And it continues like nothing ever happened. And this is called, as I kind of hinted, jump discontinuity. You can use that on your tests and whatever. It'll be fine. And one thing to note, I forgot to mention this for the previous one, sorry, is that your limit as x approaches a, it still exists. That is important to note down, because even though your function doesn't have an actual value here, it's still approaching something from this. It's approaching that same point from both sides, so that's important to keep in mind. Now with that in mind, in this case, you can see that if you do the same arrow thing, we're not approaching the same y value, and therefore your limit as x approaches as x approaches a, that the limit doesn't exist. It does not exist. However, this is kind of important. You need to keep in mind that f of a does exist. I'm just going to call this a. Sorry. Yeah, f of a does exist. So you have to keep that in mind. For these types of questions, or at least for this particular graph, f of a does exist. And I guess inversely here, limit exists, but f of a does not exist. And the last type of discontinuity is non-removable discontinuity, but it's a different type of non-removable discontinuity. And you can basically think of it as asymptotes. Like this. Something vaguely like that. It's not a perfect graph, but it's fine. I can probably do that better. That's better. That's good enough. And at x equals a, you have an asymptote. This is called, in informal terms, it's infinite discontinuity, because your limit from either side goes to negative or positive infinity. So in this case, limit as x approaches a on the left side of f of x is negative infinity. Limit as x approaches a from the right, f of x equals positive infinity, and therefore they're not equal. So all in all, limit as x approaches a, f of x does not exist, and f of a does not exist, because your function can't equal anything here because it's going to negative infinity or positive infinity depending on how you look at it. So now that we know this, we can kind of come up with an overall definition of continuity. So just write this down. I'm not going to speak this out. Okay, I probably sped that part up. I definitely will. Basically, this definition reaffirms what I just said. You have your continuous function if your limit exists, basically, and otherwise it's going to be discontinuous. That's just a formal definition in Spirit. With that out of the way, let's do some more problems, as that's what calculus is all about. So we have your function here, x squared over x. So we have to find out what the discontinuities are and where it's happening. And for these types of problems, I'll walk you through this one and I'll let you do the other one on your own, or the other ones. Yeah, the other ones. So basically how you want to first start is you can simplify this. So this simplifies to f of x equals x, but x cannot equal 0, as you can't have a 0 in your denominator, and that's going to probably fry your calculator as well if you actually do that. And the second step for especially easy functions like this is to graph it with our constraints and everything. So like this. And because it's literally just x, it's just a line that goes through the origin. There we go. Something like that. But there's a hole at the origin, because it can't exist there. So this is like your problem setup, if you're being technical about it. And essentially how you write this now is you have non-removable discontinuity, non-removable, whole discontinuity, because removable whole discontinuity at x equals 0. That's the important, but that's what you're really solving for. It's where it's happening, because you have two categories here. Your f of a does not exist, and your limit as x approaches a of f of x exists. I don't think it matters the actual value. It just matters that it exists, and these criteria match the actual criteria for whole discontinuity. I'm just going to call it that now. So now that you know how to set these things up, let's solve for one. I'll let you do this first. As always, I encourage you to solve this. Pause the video and solve it. I'll give you a second. Okay, your second's up. So let's first graph these. So it's probably like this. So that's one. I believe that should be the graph. Confirm. Okay, good. And your square root function is just this. But obviously, you need to take off half of this. Right? So, yeah. And you have a hole there. So that's your function. That's the piecewise function, how it's going to look. And with it drawn in, you can now tell that we have non-removable discontinuity again. But this is a different type. I'm also realizing that I believe I might have been incorrect about this. It's actually just removable. Sorry for that. For non-removable discontinuity, and I guess it's jump as well, as it's jumping down. At x equals 0 again, because you have a defined f of a value. You're not defined here, but it is defined for f of 0 for square root of x. And your limit as x approaches a of f of x does not exist. Alright. And I believe this is the last one I have. Yeah, and this is going to be a multiple choice problem just because why not? And this is actually a slightly different problem, but let's do it anyways. Okay, welcome back. I'll probably cut that out. So this is the problem. I'll give you a second to try it out. Okay, your time's up. And let's try to do this. So if your function has to be continuous at this point, what you basically, a step is you can first simplify this. This simplifies to what is it? X minus 1 over 2. And now it's a really easy thing because you don't have to worry about dividing by 0. You can just plug in 0 for x. And 0 minus 1 over 2 is negative 1/2. See, there was no limits. You don't even see the limit notation involved here, and you're still doing it. Limits are everywhere. Alright, they're awesome. No, they're not. And your answer is going to be B. Okay, I believe that is it for today. Let me just check. Yep, that is it. So, thank you very much for watching. Yeah, I'm the Math Fella. Make sure to follow me on Instagram at the Math Fella. And I will be back shortly. Thank you. Bye-bye.